All right, so today we're going to be going over the Chapter 18 practice problems taken from Salomon's Organic Chemistry, and this is just from my class material. So here, you can memorize the pKs if you want to try, but really the key is that the alpha carbon, the pK, is much more acidic. It's because it's directly adjacent to that electron withdrawing group, the partially positive on the carbonyl carbon. So if you lose a proton and leave electrons behind, that's going to be more stabilized. There's also the important idea of the enolate ion, where you could start with this negative here. If you abstract a hydrogen or a proton, it'll leave this lone pair behind, and it has a resonance structure that looks like this. So basically it's stabilized both by induction, because this is partially positive, and by resonance. That's going to be stable compared to over here. This oxygen has lone pairs that are going to be electron donating. So if you abstract a proton, leave behind electrons, it's going to be electron donating, which destabilizes it. So really, the closer you are to an electron withdrawing group, or if it's stabilized by resonance, the better. Okay, so question number 2 is similar. Which is the most acidic hydrogen in the compound shown? So the most acidic hydrogen is going to be the one close to electron withdrawing groups. If it's between two electron withdrawing groups, that's even better. So my instinct would be to look right here. Well, there's already 4 bonds to that carbon, and none of them have a proton. None of them are hydrogen. So you can't abstract a hydrogen from there. If maybe this methyl group wasn't there and that was a hydrogen instead, that would be a very acidic hydrogen. But instead, we have to look somewhere else. This right here is closest to the electron withdrawing group. It's a carbon with a proton. So I'm going to go with answer choice C. This is one further away. So this is probably going to be acidic because it could be stabilized by this benzene ring here, but not as acidic as this one. Same thing with this carbon number 2 over here. It's somewhat acidic, but it's one step removed from the electron withdrawing group. And then finally, answer choice A and E, or I guess that's D. Both of these are one step removed from the electron withdrawing group. So the one that's closest is going to feel the strongest effect. So I'm going to go with answer choice C. Okay. For number 3, this is going to form an enolate first, and then the enolate will attack, and you're going to get halogenation at the alpha carbon. So first, we've got, I'm going to make this just H plus for now. It will attack and form OH plus with the Br2. Okay, so we've got this protonated carbonyl carbon, and what can happen with that is if the water or something else in solution abstracts this very highly acidic proton to try and restore the H3O+, then the lone pair will move here, and this will go up, giving us the enolate form. But a lot of times, the enolate will be a nucleophile. It can act as an attacking group. And so that's what happens here. The enol, not the enolate, sorry, enol. Enolate is the ion form, enol is the neutral form. So the lone pairs kick back down to restore the carbonyl carbon, and then this double bond acts as the nucleophile, attacks the bromine, and breaks it up. So we end up with that double bond is restored. That's positively charged now. You've got your bromine has attached to the alpha carbon, plus you have a Br minus floating around in solution. Well, that Br minus can easily take this and restore neutrality, so we'll have a halogenation at the alpha carbon in acidic conditions. All right, so a lot of times you'll see that with reactivity at the alpha carbon in carbonyl carbons is that it acts as the enol, as the thing that's attacking. Once the enol is formed, that will usually become the nucleophile. Melodic ester is treated. Okay, so melodic ester, you should just memorize that. It looks like this. It's treated successively with sodium methoxide, and so that's going to abstract the most acidic hydrogen, and that's the one between these two. I think the pKa of this is like 9. So, and usually they'll use this sodium methoxide, looks like this. It's got an Na plus counteracting the O minus. And the reason they use that is because if it attacks the carbonyl carbon by chance and does a substitution reaction, it makes the same thing, so it doesn't matter. This would attack, kick up, come back down, kick this out, and you just have the same ester, basically. So it doesn't impact this over here, so it'll react somewhere else. So it'll steal that. Sorry, that's an arrow my pen like dragged. And then this right here will make a lone pair, so you'll end up with, and you're going to see this reaction over and over in this chapter, a lone pair right here. And then this lone pair will be used in an SN2 reaction. So you'll have bromopentane, that's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 with a bromine. So it'll attack and kick out, and you'll end up with alkylated 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Make sure to count your carbons here because it gets messed up all the time. Melodic ester. And then actually they'll use the potassium butoxide, which is a little bit stronger of a base, to attack and do the same thing. Deprotonate. One, two, three, four, 5. And then your lone pair will be treated with iodomethane. So it attacks, does another SN2 reaction. So you're left with, so this is basically just using the acidity of this melodic ester to do an SN2 reaction and make it a nucleophile. Then we use hot aqueous NaOH and HCl. It replaces your ester groups with a carboxylic acid. And then with heat, that will get rid of one of your carboxylic acid groups. And so you basically end up with a carboxylic acid that 1, 2, 3, 4, 5. This is most often where I see people lose their carbons. So from here, you have 1, 2, 3, 4, 5, and then a methyl group. So basically, you can, using this synthesis, get a carboxylic acid with any alkyl groups you want on it. So that's what makes it useful. So that's a melodic ester synthesis. You're going to see that a lot in this chapter. Like I think there are probably 3 or 4 of these at least at the end. Ooh, yay, another acidity question. So which is the most acidic hydrogen in the compound shown? That's going to be the one between 2 electron withdrawing groups. So this pKa of a alpha carbon proton right off of just a regular old ketone is about like 19. But if it's between 2, the pKa is like 9 to 10, I think, somewhere in that region. So it's much more acidic. These over here are just going to get closer. The further away they get to the from the withdrawing groups, the closer they'll get to the pKa of 50 that normal sp3 hydrogens are at. So this is the right answer for this one. And it's actually the same thing here. With the cyano group, you're going to experience the exact same thing. This is just another electron withdrawing group, and arguably the effect will be even stronger because it's right off of that carbon where the electron withdrawing group is. So this is the same type of thing. They've just replaced one electron withdrawing group with another one. These will probably be closer to the 19 to 20, and these will probably be closer to like 30 or 40. All right, so lots of acid questions on this chapter. Number 7, considering the highlighted hydrogens, list the following compounds in order of decreasing acidity. Okay, so if you just know off the top of your head the pKa's, that's going to be helpful. Alcohol is 16 to 18. It's close to water because water is kind of like an alcohol. Carboxylic acid is 4 to 5. And an alkyne is going to be 25. At the alpha carbon, it's going to be around, I think it's like 19-ish. And then for the diketone, I think it's going to be around 9. So if I was arranging this, I would say the diketone and then first the carboxylic acid. then the diketone, then the alcohol, the alpha carbon, and then the alkyne. So if that's the right order, you can just eliminate any one that doesn't start with 4. So if you just know that this acidity is more acidic than any of these other ones, which is a carboxylic acid, so it's an acid, so it's going to be very acidic, then you can already eliminate 3 of the answer choices. And then it's just a matter of, do you know that an alkyne is going to be less acidic than a diketone? And then you can narrow it down to the right answer. So the right answer is answer choice C. Okay, for number 8, which represents an ester enolate? Enolate is different than an enol. So the enolate is the ion, the keto-enol form looks like this. This is a tautomer, and an atom is actually moving. There's 3 hydrogens here, and one actually, it's almost like a reaction within itself. The oxygen steals one of these, and the lone pair moves down here, and this comes up, and that's how we end up with this. That's different than resonance, which takes place when you have an ion, right? If you have an ion that looks like this, no atoms are actually moving when you kick this up. You just have electrons moving. So that's the difference between the enolate ion, the resonance structure, and the tautomer. So when you're looking for these, you want to look for these basic structures. If it's a keto-enol, you want a ketone with a hydrogen that can be removed to make the enol. It's called an enol because there's a double bond here and an alcohol, so enol. For the enolate, you want a lone pair at the alpha carbon, and then an oxygen with a double bond with an oxygen with a minus charge with a double bond between what used to be the carbonyl carbon and the alpha carbon. So this doesn't have a double bond in the right place. It would need to be here. So that one's wrong. This looks good. We've got a lone pair down here, giving it the negative charge, and a ketone with a double bond. So that is a possibility. Same thing here. We've got the double bond and an oxygen with a minus charge up here. So that's good. Double bond between the carbonyl carbon and the alpha carbon, and a minus charge at the top. This has the minus charge in the wrong place, so that's not going to work. So that leaves us with answer choices B and C, so the right answer is E, 2 of these choices. Now this is a keto-enol pair, so now we're looking for an alcohol where there's a double bond 1 carbon away, or what used to be between the carbonyl carbon and the alpha carbon, and then the other one is a ketone with an alpha hydrogen available. So what I see wrong with this one is there's not a double bond right here, so that one's wrong. This one looks right to me. We've got the ketone with an alpha hydrogen that can be removed, and then a double bond with an alcohol adjacent. This has 2 alcohols, so that's not right. This is close. The double bond needs to be right there instead, and then it would be right. Same thing, this and this are the same structure, so the double bond just needs to be there instead. So the right answer should be answer choice B. Which of these compounds would exist in an enol form to the greatest extent? Okay, this is kind of a weird question, but basically it's asking which one would be more stable if it was in the enol form. And there's usually 2 instances where this comes up. If you have a diketone, really a diketone is happier and more stable in this form. And the reason for that is because of hydrogen bonding. So I'm going to redraw it in another form. The intermolecular forces here will give you a nice stable 6-membered ring that is more stable than if you had 2 ketones with all their lone pairs right next to each other. So this is just a more stable form of the diketone. The other time that this comes into play is if you have a resonance structure, and being in the enol form would make it's not really resonance, so it should look more like this, an aromatic ring. And when that's the case, this is going to be more stable because aromatics are more stable. So the only one of those where that is a possibility is with this diketone. So your answer is answer choice B. Oh, this is the perfect follow-up. So this is the same kind of thing where you can see if this right here was in the enol form, there would be a double bond there, and that would make it an aromatic ring with an alcohol on top. So this is the other one we look for. Now, these two so close together, I'm not sure if it would result in the oxygen, the enol form, but I would think the problem would be that it wouldn't be a 6-membered ring, it'd be a 5-membered ring, so it wouldn't be as stable. And because of the structure of this ring, they're pointed in opposite directions, so they were not going to be able to form that same ring. So I wouldn't say that one's stable. This one, I mean, in general, in general, enols are not as stable as ketones because the carbon-carbon double bond is not as stable as the carbon-oxygen double bond. So there's nothing special about the rest of these that make them want to be in that other configuration. So the only choice that makes sense is answer choice C. Which of these halides is predicted to alkylate malonic ester in the highest yield? Okay, this is a lot of crazy words. But if you remember, the malonic ester looks like this. And to alkylate it, we use a base to make it have a lone pair there. And then it does what? It undergoes an SN2 reaction. We had the bromine, and it just came and attacked and kicked that one out and formed the alkylation. So this question is literally an SN2 question from chapter 6. It's guised as something so much more complicated. But really the question is, which one of these is going to react fastest in an SN2 reaction? And if you remember way back then, primary reacts the fastest because there's less stereochemistry or steric hindrance. It's going to keep it from reacting. It's not as bulky. So this is going to react quickly. This is a benzene ring, so it doesn't undergo SN2 reaction. This is a tertiary, so that doesn't happen. We've learned about that. So none of these are really going to go as quickly as a primary. So answer choice A would be the best option. Okay, question 13. This is what would be the major product of the following reaction. So I think this is going to be, it won't be a haloform reaction. I think it's just going to be halogenation at the alpha carbon. So we did a similar question to this earlier. So the enolate is going to form first. The base is going to abstract here. Oh, this is not drawn out well. I'm just going to draw it back out for you. Okay, at the alpha carbon, we have a methyl group and a hydrogen, and then another carbon here. Okay, so the base is going to abstract here. This will go here and kick this up. So we've got the enolate ion, and that's going to react. Now, if it's easier for you to think of it like this, you can draw this out and then this double bond being the attacking. Or, sort of a shortcut I've learned that is also correct because it's just a different resonance structure, is you can just leave the lone pair right there. So the base abstracts the proton and it goes right there. You need to know that the resonance structure exists between these two, but either of these is equally correct. Either way, it's going to attack from right here, and it helps me just remember that it's going to attack from right here when I draw the lone pair like that. And the thing it's going to attack is going to be this bromine. So the proper arrows, if you're doing this forms, they would come down and then attack, same way like that. But it just helps me to remember where it goes if you draw the lone pair right there. So we'll have the bromine plus Br minus is going to be in the solution. Usually that Br minus is going to be canceled out when you just add some acid or something to the solution. So I think the right answer choice here would be answer choice. Let's see, whichever one has this has a bromine on the benzene ring. So does this one. You guys learned how to put a bromine on the benzene ring, chapter 15. That needs a Lewis acid and a halogen. So that's not going to be right. You should know off the top of your head, neither of those is going to work. So then now we look at where the alkylation happened. Well, none of these really make sense. If it was a radical reaction, it would go to the most stable. These aren't the most stable, so I'm not even sure how would we get these. So the only answer choice that makes sense is answer choice C. The next question is really tricky, and it's just about if you really understand the mechanisms of the enolate ion. So hexanal is an aldehyde. I remember aldehyde by al at the end. Aldehyde, 1, 2, 3, 4, 5, 6. Is that right? 1, 2, 3, 4, 5, 6. Yes, okay. 1, 2, 3 dimethylhexanal is treated with NaOD. So OD is roughly equivalent to OH minus, but they just want to basically track where that deuterium, which hydrogen is going to be replaced. So this is how they get at mechanistic questions without actually asking a mechanistic question. So it's going to attack, and you can either just stop right here and have the lone pair go there, or you can have the lone pair form the double bond, kick up, and see the resonance structures of the enolate ion. Both of these are correct. Both of these are legitimate forms. I like this one better because it's easier for me to track. And then it's in D2O. So likely this is going to attack the deuterium, and you'll end up with a deuterium right there. And that really is basically a question that's just asking, can you track where things go when they're in a solution in the enolate ion? Do you know how the enolate ion acts, moves? Do you understand that which hydrogen would be abstracted, all that stuff, without having to do it for your response question? So this is going to be your answer. And so it's not going to replace the aldehyde, so those are wrong. This doesn't do anything with the enolate, so that's not going to be right. So the answer choice that makes the most sense is answer choice D, right? At the alpha carbon, the acid is abstracted, and then the nucleophile that's formed attacks. Okay, question 15. What would be the major product of the following reaction sequence? Okay, so usually when we see a ketone with a halogen, it's going to be a halogenation at the alpha carbon. And this happens with acid or base as the sort of catalyst, as the thing that's functioning the reaction. So I showed you an alpha base, alpha halogenation in the last, I think it was question 13. But now I'm going to show you the other one. So usually if there's an acid, the first step is going to be protonation of that carbonyl group. So you end up with this. And then it will be very easy, because this is already protonated, for this base to come along, or even the water probably from here might do it, and abstract this hydrogen. So whichever one will come, and it will form, it'll just come and take that, and it will form the enol form. This double bond formed, this kicked up, and you have an alcohol. So now we can see the enol will be willing to attack, especially in these basic conditions. It'll come down, attack that bromine, and kick out. So if your OH plus and your Br plus, Br minus, this Br minus could easily come and take this, and you'll end up with the halogenation at the alpha carbon. So probably the base here is going to be what abstracts this acidic proton, but water could maybe even do it too because it's relatively acidic. But in basic conditions, that would be what happens. And then we have, actually, so I guess this is the first step, and we make this. So if even in water, this will abstract, so you can get this form. But then if you add another base and heat, that's tricky. If you add another base and heat, it's going to go through an elimination reaction, because that's just chapter 8 stuff. I think it's chapter 7 or chapter 8. So if you have a base and a good leaving group, the base will come and it's going to attack a hydrogen from this side, not this side, because there is a proton available over there. There's not one here. This will go here, and you're going to end up with, that's tricky, a double bond, one away. So I think the right answer choice is actually going to be answer choice B. That's very tricksy. This answer choice C would not occur because the base needs to be obstructing the proton one away from the leaving group, so that wouldn't work. This is the answer after step 1. That's tricky. I almost chose that as the right answer. And then I didn't realize that these were 2 separate steps at first until I saw that heat, and it triggered the elimination reaction in my mind. And then this one's wrong, yeah, because it's one away, the double bond. This has replaced the carbonyl carbon with bromines, which we've never seen that happen. And this abstracted the proton from here, but there isn't a proton there to be abstracted, and it replaces the carbonyl with the bromine, so that doesn't make sense. Tricky. These 2 answer choices are very tricky. Okay, this next one is a fun one. It's a haloform reaction. So just like we've seen in this last few, if you have the base, it'll form the enolate. Which I'm going to draw like this. Forms the enolate ion, and then you have this I minus, and it'll break up, and you'll get the iodine that goes right there. It's funny to draw it upside down. And basically what happens is that'll happen 2 more times because you have 2 other alpha hydrogens here. So these 2 other alpha hydrogens will also be replaced with iodines, which then makes it a good leaving group. It undergoes the same mechanism as the last iodination of the alpha carbon. You'll have to have excess iodine for that. And you have to have 3 alpha carbons for this to take place. And then your acid will actually come in and attack, or water will come in and attack and replace. If you have the OH minus, that minus is in the wrong place. It can come in, attack, and then when this recollapses, this has become a really good leaving group. So either the OH or water can do that, either one. If it's water, you'll end up with this OH2 plus here. And then you have the Ci3 minus in solution, which would very happily deprotonate that and give you carboxylic acid. So that's a kind of complex reaction mechanism. I think it's worthwhile to know it. But basically, the iodoform reaction will make iodoform, just like chloroform or bromoform. It's 3 iodines or 3 chlorines or 3 bromines and then a hydrogen there. So the byproduct is actually the iodoform. It's Ci3H. That's your iodoform, and then it leaves behind a carboxylic acid. So I think it's worthwhile to know that. It's a little complicated, but you should be on the lookout for it. And this is a follow-up question to that. Which could be subjected to a haloform reaction to produce M-chlorobenzoic acid? Okay, so M-chlorobenzoic acid. Benzoic acid looks like this. Ortho, meta, para. So M is meta. Ortho, meta, para. So M-chloro, benzoic acid. So the only thing that would work to get a carboxylic acid there is if it had, if it had a CH3 group, and the chlorine shouldn't be affected, that could undergo, each one of these H's would be replaced with a chlorine or iodine or bromine to swap out to become Ci3, CBr3, CCl3, and then the attacking group, either water, probably water would come and attack and kick this up. It'll come back down, kick that out, and give you a carboxylic acid. So the only thing that would work would be a meta, I guess, what was that? Acetophenone, metachloroacetophenone. So that would be this one, I think. Is that right? I think so. I have it rotated slightly, but that should be the same answer choice. Okay, So the chloroform reaction or the haloform reaction, iodoform, all those are worth knowing. But remember, it produces the chloroform or iodoform as a byproduct, and it leaves behind a carboxylic acid. Okay, LDA is interesting. It's a good base that goes at the alpha carbon. It's a good base that goes on the alpha carbon. It's going to go on the less substituted side. This lithium diisopropyl aluminum hydride, I think is what LDA stands for, but it has two isopropyl groups that look like this. So, two big bulky groups on it. And then because it's so bulky, just like what we saw with the Hoffman product, it's going to go to the less substituted side. So instead of stealing this hydrogen over here, it'll steal this hydrogen over here. So that's really what makes it useful. And it's really just going to, boom, steal that base. This is negatively charged, or steal that proton and make the enolate ion. Sorry, I'm slipping over my words today. So you'll end up with your enolate ion, and of course that will attack. In this case, it looks like we have a SN2 reaction. So this comes back down and attacks here and kicks out, and you'll end up with it attacks 1, 2, 1, 2. So this is where I think it comes in handy if you want to draw where the ion forms like this, because that helps me remember how many carbons. So this is equivalent to this. These are resonance structures. They're the same thing. But thinking of this coming down and attacking helps me know, okay, I'll have 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons should be right. So it just helps me to keep track. But like I said, either one of these would be correct. So you can do either one. I prefer this form for keeping track as the attacking one, but as long as you have both structures on like a free response question, that would be fine. So let's see which one is the right answer here. You need to have 4, 1, 2, 3, 4. I think it's answer choice A. I always get nervous when it's the first one. This wouldn't be right because I'm not sure why that would have formed down there. This one, yeah, none of these other ones look right at all to me. They're not even anywhere close to this. So the only right one would be answer choice A. Okay, 19. So alcohol with PCC, this goes way back, but hopefully you remember, way back like 2 chapters, oxidation. It'll turn a secondary alcohol into a ketone. Then we use LDA to form the less substituted. If you want, you can draw the LDA abstracting the proton, the bond coming up and kicking up like that if you want to. Either one of these is correct. Either way, the attacking happens from right here. So the LDA comes, you can draw the hydrogen getting extracted and the lone pair going right there, or you can draw the full resonance structure. Either of those is correct. And then again, we just have an SN2 reaction. So it's going to, either one of these is right. You can draw this coming and this attacking over here, or you can draw this attacking step. Either way, it's correct. And then you have, so this is the attacking carbon, 1, 2, 1, 2. Okay, so the right answer choice should be answer C. The reason D is not the right answer is because the LDA won't abstract from the more substituted hydrogen. And the rest of them are just kind of crazy. The only other contender is pretty much this one. These just don't go through the proper steps. Sometimes it's easy to point out like, oh, this one tried to do this one tried to do this, but those are just kind of crazy. Okay. So this reacts with phenylhydrazine and gives a positive iodoform test. The compound could be which of these? Well, for a positive iodoform test, we know that we at least need to have an alpha carbon with 3 hydrogens. That's very important. So we know at the very least it needs to look like this. So that gets rid of the aldehydes. This one doesn't even have a ketone at all. I think it has an oxygen in the middle. So if you just know that an iodoform needs that, then you can narrow it down to answer D. The other thing this is asking about is phenylhydrazine, and phenylhydrazine reacts with ketones. Basically, it's a test for ketones. We didn't really talk about that in class, so I don't know if you really need to know that. It's worthwhile to check it out, but for this question, you can answer it just from knowing what an iodoform test looks for. So answer choice D. Okay, for 21, we start with bromine. Add magnesium. That's going to give you a Grignard reagent. With Grignard reagents, I just go ahead and take it to the equivalent anion because that's easier for me to visualize. And that reacts with carbon dioxide. Hopefully you did this one in lab. I love the Grignard reagent lab that we have on this campus. 1, 2, 3, and then another carbon right here. So you should have done this where you formed a Grignard reagent where you drop metal in a little test tube, and then it reacts with dry ice to make carboxylic acid. So you put it on dry ice, and then you add acid to it, and it makes carboxylic acid, which is pretty cool, I think. Did I lose a carbon anywhere? 1, 2, 3, 4. Okay. 1, 2, 3, 4. No, my carbons are good. Then if you react with Cl2 and P, basically what that makes is PCl3, and that's going to replace your carboxylic acid with the chlorine, but also it'll chlorinate at the alpha hydrogen. I don't think you need to know the mechanism for that. I'm not even sure if it's in your slides. Go check it out. If it's in your slides, you're probably responsible for it, unless Dr. Berhe specifically said otherwise. But so it will replace this with the chlorine and here, but because we learned in the last chapter, if you have an acyl chloride and you react it with water or acid, it will go back to a carboxylic acid. You can end up with, it's basically just another way to add a halogen at the alpha carbon. That looks like Hg. It's not mercury, it's a carboxylic acid. So the right answer for this one should be answer choice B. This replaced the wrong chlorine. This never used the water step to turn this into a carboxylic acid. This is just all kinds of crazy, and so is this. So there you go. Okay. For question 22, what would be the major product of the following reaction sequence? So PCC makes a ketone. Then you use LDA to form a base on the least substituted side. So I just went ahead and drew the lone pair here. You can see how I did that in the past few questions that used LDA. And then it's simply going to be another SN2 reaction. This is a really common one in this chapter. So you'll end up with, the big thing is not losing your carbons. 1, 2, 3, 4. 1, 2, 3, 4. So you'll end up with a chain that looks like this. So I guess the right answer is answer choice A. Is that the same one we already did? I think so. Oh well, you got to see it twice. This is another melodic ester synthesis. So this OET is negatively charged. It's going to come and take this very acidic proton and make, if you want on this, you can draw the enolate form as well, but I just draw the lone pair. That's a hydrogen, not an iodine. And then reacts with phenyl bromide. So the SN2 reaction takes place. It's 1 carbon away from if this carbon was right on the bromine, this wouldn't work. But because it's off of this CH2, it's just a regular old SN2 reaction. Still have a hydrogen over here, and then a bond is formed to this CH2, and then your benzene ring is there. So make sure you don't get too many carbons. That always happens in this kind of a problem. And then they go, they don't do another alkylation. They go ahead and replace this ester with a carboxylic acid. And then with heat, you lose the CO2, and basically you've added 1, 2, and then the benzene, 1, 2, and then the benzene, 1, 2, 3, 1, 2, 3, and the benzene will be over here. You've basically just added a benzene ring to an alkyl chain onto your ketone. So you've just alkylated a ketone however you want. So the right answer on this one is answer choice C. I always see students going for answer choice A for this because they've lost their carbons. I almost did it too when I was counting up. You saw me. So be sure that you're counting up your carbons and you're not losing any on all these melodic ester questions. If you know how to do the problem and you get it wrong just because you counted up the wrong number of carbons, that sucks. So just try to be on top of those. Okay, for number 24, this one's a little different. So you have two equivalents of the ester ion already formed. And then you have this one equivalent of this halogen. So actually what's going to happen, first this will attack, and you end up with one carbon, two carbon, and then a bromine. Okay, so you'd think that would just happen a lot, right? But there's no more of these out in solution after this has taken it up. And there is another one of these. So actually, this is going to attack on the other side and kick this out. So you end up with this crazy structure. Oh, I don't know why I did this in both places. Looks like this. Make it a triketone or something crazy. You have another one of these on the bottom. So it's made this like wild structure. And then all these are going to be reduced to OH groups. And then you have the decarboxylation with heat minus CO2. So that's going to get rid of only one. You have to have the adjacent diketone. It's going to get rid of only one from each of the sides. So then you end up with a crazy long chain with carboxylic acids on either side of it. Did I lose one? I think I did. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Need to draw one more. 6. Okay, and that is going to be your final structure. So you can still get 2 carboxylic acids on either side if you want to. And the only one that's even close to this structure would be this one. 1, 2, 3, 4, 5, 6. That's right. I like to just count my carbons just to make sure. This one's kind of close, but it doesn't have the carboxylic acids. These made these crazy rings, so answer B is your right one. Okay, and the very last one, this is another ester, melodic ester question. Looks like this. And then they use the base to get a lone pair right here, and then they react with ethyl bromide. So it's the same exact type of question. Again, you make a nucleophile and then you just do an SN2 reaction. It's easy as pie. I guess I shouldn't say it's easy as pie. It's consistent as pie. Just you keep getting that same problem over and over where we're in this chapter where we're making a nucleophile and then just doing an SN2 reaction. So then we use the tert butoxide to make another nucleophile, and then we do another SN2 reaction. No surprises here. Then we use heat to convert to a carboxylic acid. And then we do decarboxylation. 1, 2, 1, 2, 1, 2. and end up with 1, 2, 3, 4. And on this one, we have a methyl group. And I believe that would be, let's see, answer choice D. And for these, you could solve these problems pretty much as long as you know that once you apply the heat and do the CO2, you're going to get a carboxylic acid, and that's going to go away. The only one of those that has that looks like answer choice D. So you can use that kind of thing to eliminate wrong answers. Okay, well, that's it for this chapter. I hope this was helpful for you. Good luck studying for your exam, and please feel free to comment if you have any questions. Share my channel with whoever you think it will help. Thank you.